then oh yes, let's record it. So so what we want to do is then find the infimum of the energy over that space of homomorphisms. Okay. Now, if P is greater than N, it's been proven that F is coercive and lower semi-continuous. And then therefore you can find a minimizer, or well, a minimizer exists. When P is less than N, it's been shown that the LSC, the lower semi-continuity property may fail. And for P equals 1, you're not even coercive, in the sense that, let's say, a weak limit of a W11 map should not necessarily be in W11. I mean, it could exactly be BV. So, I don't know if any of you have seen the sitcom from the BBC, which was on the TV when I was a kid, called Dad's Army. And this guy, this is about the Dad's Army is like, in Czech it's called Domobrana. So these are just the guys who are too old to go to the war, and so they stayed at home and they were training for when the Germans are going to come. And this guy was always like, oh, we're doomed. He had a Scottish accent, we're doomed, we're doomed. And there was the other guy who's like really nervous. He's like, don't panic, Mr. Anning, don't panic. So his advice is to relax, okay? So we look at the relaxation then of this energy when specific, okay, so let's take an energy F which has linear growth. Specifically, we could just look at the absolute size of the differential matrix, right? Just say that's our energy. So then we can make a relaxation of this, and it's going to look something like what we've got there. So you've got the quasi-convex envelope of the energy density, and you've got the recession function of the quasi-convex envelope, which is applied then to the singular part. So when you start to get jumps and fractures and this sort of stuff going on, so then we basically say, okay, let's look at this particular direction. How much do we have to penalize that direction? And then integrate with respect to the singular part of the measure there. Okay. So it's been proven that this relaxation is in fact continuous with respect to different types of topology on BV, right? So yes, and with other different boundary values as well. Which, let's say, our current research is not quite up to discussing more complicated boundary values. At the moment, the results which we have, we're just going to say, okay, let's say we're identity on the boundary of a square, unit square, and then let's see what happens inside. So what happens with more complicated boundary values? That's still a little bit open. Okay. So, seeing as we have a continuous relaxation of our problem when we have, let's say, just a linear growth of the energy density, and we have this relaxation, we know that it's continuous with respect to strict and area strict topology on BV, which I'll explain in a minute. Then we'll say, okay, we're naturally led to look at the various classes which arise, because, okay, so it's going to be in BV, fine, good for you, but the question is, will your limit map do you have any reason to say this is something reasonable in the context of nonlinear elasticity? So originally we were saying we should have something like homomorphism. Okay, of course, we can easily get discontinuity. So we can get fractures, we can get also cavities being created in the body, of course. But the question should be, do we get something which is, let's say, somehow reasonable or not reasonable? Is it possible to take two parts of the body and then put them sort of onto the same place? Like not just one point and one point, but let's say, can I take a set of a ball over here and a ball over here, and in the end, in the limit, they overlap, right? This would not be reasonable as a model in elasticity. So also we've got various different topologies on BV maps. And the question is, do the classes which we get when we take the closure of the homomorphisms do they coincide, right? So strict convergence is when we assume that we've got weak star convergence and also the total variation converges. So we know the total variation is lower semi-continuous. So the variation of the limit is going to be less than or equal to the limit of the sequence of variations. But if in fact we get actually down in the limit to the value of the variation of the limit, then we can say it's strict convergence. And area strict convergence is if also we can split up the derivative of the approximations into two measures. Let's say one measure is absolutely continuous, and it in fact converges strongly in L1 to the absolutely continuous part of the derivative, and the second part converges strictly to the singular part. That's what I'm going to be talking about when I say area strict. Okay, so obviously area strict is stronger than strict convergence, because you're also wanting that the absolutely continuous part converges strongly in L1. But it's not necessarily, okay, just because you're converging strictly doesn't mean you're converging area strictly. So what you've got to imagine is like a staircase like this, which is the stairs are getting smaller and smaller each time. Okay, sure, I'm converging strictly to this linear function, but not area strictly. Because basically on the left I'll always have like some kind of sum of Dirac's, which is okay. So it's not going to be converging strongly in L1 to, and even if you say okay, let's make something which is not quite like this. It's not like literal Dirac's. It's just going to grow very quickly. It's still not going to be converging area strictly. So, but it'll be converging strictly. So. Okay, so what are the known results when it comes to the closures of of Sobolev homomorphisms so far, right? So one thing which was proven by Ivanets and Onyinen is that when you've got p greater than 2, so you're already guaranteed continuity, then you're in the case of monotone maps. A monotone map, let's say the easiest way to understand it is a monotone map is a map which can be approximated uniformly by homomorphisms, right? So things become a lot more difficult when you go into like this subcritical territory, because all of a sudden you've now got discontinuities. And okay, so your first okay, what a lot of people thought would be the correct condition would be that you would have the inf condition. Now the inf condition means that when you're mapping a ball, the outside goes to the outside and the inside goes to the inside. But in fact, in this paper by Philippus and Campbell, it was shown that that's not enough. In fact, you can somehow twist something around so the outside is still going outside and the inside is still going inside. But what you've done is you've taken a line and tied a knot in it. And then it's impossible to approximate this by homomorphisms now. So what they actually came up with was a different condition called the non-crossing maps, which basically means it's impossible to tie a knot in a line. So you take a line and you can't tie a knot in it. What does that mean? Well, the restriction of the mapping to any, let's say, one-dimensional grid can now be approximated uniformly. That's the easiest way to explain that. And okay, already in this case you can have cavitations, and that's okay. If you don't have any cavitations, if your limit map is continuous, then basically nothing surprising is going to happen. But as soon as you get cavitations, the whole thing can become, like, let's say, somewhat delicate. And this is where these very counterintuitive examples of inf maps, which can't be approximated by diffeomorphisms or homomorphisms, come about, right? So this is more or less what the NC condition says, which I was saying. But you take basically almost any grid, which is like one-dimensional lines in one direction, in the other direction, and the image of the grid, which is going to be, okay, it's going to be collapsing in onto itself, but you can always find an injectification, which is arbitrarily close in the uniform sense to what the original map was doing. So you're assuming that your map is now continuous on the restriction of this grid. His image is something, but something which is possible to untwist and untangle so that you get something now which is injective. So that's this NC condition. And it was proven, which was on the previous slide, it was proven that the closure of W1P homomorphisms is precisely this, maps between W1P and satisfy this non-crossing condition. Okay, so it's something actually stronger than the inf condition, which in the end comes out quickly once you know that this is, okay, everything which is in the closure will have to satisfy this inf condition. And if you know that the Jacobian is positive, you don't actually need to use a grid of lines, but you can just use one line. So whenever you can injectify the image of one path, then you're already you can injectify a grid. But if you don't know that the Jacobian is positive, in fact, just being able to injectify one path is not enough to say that you're in, which is also not enough to say that you're NC as well, right? So these are some examples which we put together and which were in Guido and Aldo's paper as well. Okay, yes, but the point is you're in the weak closure if and only if you're satisfying the NC condition for W1P. Okay, let's say for P greater than 1 and less than 2, right? So the question is what happens still. The question is what happens when we get to the BD case. So one thing is known: it doesn't matter if you're using homomorphisms or diffeomorphisms to approximate, because whenever you've got a homomorphism, you can approximate it with a diffeomorphism, which is like, let's say, not particularly easy, because just taking, let's say, like a convolution approximation. Whenever your map is twisting, the convolution approximation just tends to go like the shortest route, and you get things crossing over, right? So that's no good. But if you take some very careful construction, you can find actually a way for a homomorphism in W11 to approximate it by a diffeomorphism in W11. This is so-called Ball-Evans approximation question. And the same is true if you're working in BV. So whether you're taking the area strict or the strict limits of homomorphisms in BV, or you're talking about the strict or area strict limits, and you assume that they're diffeomorphisms, then it doesn't make a difference, right? So the two things are the same, and these are the classes which we're left to study. So that's what I'd like to present today. So what's not particularly clear is when we have a point, we have to define an image of the point, right? So this was first studied by Laura and Spector, but also Hannah, Moore, and Corral. They also made models of this. We have to define something which is a topological image, right? So if we have, let's say, so imagine you've got some kind of a rubber cylinder and you start twisting it. What will typically happen is there'll be cavities created inside. Now we would like, okay, what we would really like to have is a homomorphism which goes from omega onto delta. But we don't necessarily have that because then we've got a cavity. So what we'd have to say is, okay, we'd still want to say that somehow it's filling. So we'd say the image of one particular point, which is where the cavity emerges, that's going to fill the entire cavity in the image, right? So what we have is an approximating sequences of BV homomorphisms. And we use this sequence to define an image. So what you eventually see here is some kind of a limb sup. So take a point and take a small ball around it, and then take the image of that ball and take a slightly larger neighborhood of that set. And then say, okay, let's take the lim sum as over the sequence. That's more or less what's happening. Okay, so if you imagine that you've got a ball and your series of functions is sending, okay, sometimes it's sending it off in that direction, sometimes it's sending it off in that direction, sometimes if it keeps on doing this, then what you'll eventually see is, okay, well, the image of this ball then is all of this. It's kind of a lim sum type argument. Okay, so what happens is when you've just got weak star convergence, this is not really a good idea, because what happens is, okay, in this sequence, what we're going to do is take a rectangle, and F1 is going to take this yellow part and stretch it onto the yellow part over there. And as you go, you'll start stretching a smaller and smaller yellow part onto a longer and longer yellow part, right? So what happens is in the limit, and the limit ought to be identity, because basically in the end, outside of basically the line, I'm not doing anything, it's just all identity. But what happens with this definition for the image is that you start sending one point onto a line. Okay, so using some argument like this, a little bit like what I said over here, you can actually take a point and send it onto a ball. But at the same time, you're basically doing identity. And let's say the image of the ball is containing the image of this red ball. So this is bad for us, because what we would like is that the image of two different sets are essentially disjoint. Okay, if they coincide on a set of zero measure. If the images of the sets are coinciding on a set of positive measure, this is basically the interpenetration of math, and this is no good for us. So then we could say this is not a reasonable model for elastic deformations. So when it's just a weak star closure, this is no good. So we definitely need something stronger. But what we proved is that, okay, I say strict, it's actually something a little bit weaker than strict. So I'm talking, when here we didn't actually study the class of the strict closure of BV homomorphisms. The closure was strict in the sense of D1 of F was converging strictly, so the x derivative of F, his variation was converging strictly, and D2 of F, so the y derivative of F was also converging strictly. So it's like some kind of a Manhattan version of this. So okay, similar but not exactly the same. And what we found was our topological image is a natural extension of the one defined by Miller and Spector, where they were involved with this inf condition. The topological image of disjoint sets is essentially disjoint, so we don't get this business where two different sets can then have images which overlap, and their images, the overlap of their images have positive measure, and you have a distributional Jacobian, or something like that. So, okay, yeah, well, you have a measure which turns out to be the distributional Jacobian. It does actually exist, and it allows you to, whenever you've got a cavity which creates a hole of positive measure, then this Jacobian will tell you, okay, here at this point now you've created a cavity. Also, we were able to model not just cavitations but also fractures, and we proved that the fractures, right? Okay, it's a one rectifiable set, and you have some bound on the edge. Okay, fine. So essentially, when in this paper we proved that, let's say, strict limits of BV homomorphisms, they're reasonable models for elastic deformations, but we don't really know exactly what they look like at this point. Yes, okay, fine. So here I defined you a topological image. It seems to be depending on the sequence of the approximating sequence. Actually, it doesn't depend on the approximating sequence. Okay, and yeah, the image of a point has some nice properties, and the map is differentiable almost everywhere. Yeah, fine. Okay, it's not all that important, I think. Well, it's very important. Is my result, but we can skip over the details for today. Right. So let's go back to these non-crossing maps, because now I want to tell you about how we classified these strict limits of BV homomorphisms. So the De Philippis Fratelli non-crossing condition is basically that we can take a grid and we can injectify it, right? And this is identical with being in the W1P closure of homomorphisms, right? So our idea should be, let's say, expand this concept, basically use this non-crossing concept, but the problem is that there are no uniform continuous approximations because you can't avoid the fractures. So make your one-dimensional grid. You can pretty much expect that it's going to cross some fracture somewhere if a fracture exists, and why shouldn't it? And then your restriction of your map to this grid is not continuous. So how do you want to approximate it uniformly with a continuous map? It doesn't exist. So we definitely need to extend this concept. So how we do this is we use our concept of a topological image, which we developed in the previous paper, to say, okay, well, actually what happens when we meet the fracture is the topological image, it just goes in a straight line from one point to the other point. Okay, so now if we do a suitable reparametrization of this curve, which happens whenever we meet the fracture, we replace what's missing just with a segment and say, okay, now that's the shape, and now let's just reparametrize it. So let's say we're going constant speed, and then we have something which is, let's say, continuous. So now we can talk about uniform approximations. And then we say, okay, so this map needs to satisfy the NC condition. So if I try and draw a picture, it should look a little bit like this. Let's say we're working on a square. In the pre-image, we've made some grid. And okay, so the one-dimensional restriction of our BV map is somehow reasonable on this grid. It's still a one-dimensional BV map, but there are some places where the map is jumping. So we need to work on each square individually. So we go on the boundary of each square. Okay, so the normal image is doing something like this, then it's jumping over here, and then maybe it's coming back over here, and then it's jumping again. So we connect these up with lines. We say, okay, I've got one corner here, one corner here, one corner here, one corner here, and it's probably here, 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 here. What you know is that you're always continuous at the corners, which is necessary. And then you say, okay, well, I'm now going to map this part onto here at constant speed, this part onto this curve by constant speed, this part onto this curve by constant speed, and so on. Right. Now I've got let's say a continuous map from the grid onto what I say ought to be the image of the grid. And so then I say, okay, this has to be, you have to be able to approximate this uniformly. And that's what we call the NCBV condition, right? Yeah, so this is a little bit like the picture which I was drawing you a second ago. There are jumps, but not at the vertices. And you want to be able to, yeah, so whenever you've got a jump, which corresponds to, basically over here is a fracture, and so it's creating some straight line here. So we say, okay, well, fill it in, reparametrize it, and then find something which is going to injectify the image, right? So this is exactly like the NC condition, except first we fill it in, and then we say, okay, this map needs to be arbitrarily, accurately, uniformly approximatable by injective map, right? Okay. So this is the first result which we came with, which says that, okay, if you're a BV map, okay, on the square with identity on the boundary, so we're just wondering what's happening inside, and we satisfy the NCBV condition, then your map is the Manhattan strict limit of homomorphisms. So it's possible to approximate F by a sequence where the D1 of Fk plus D2 of Fk, that is converging strictly to D1 of F plus D2 of F. Conversely, if F is in BV, which is the okay, let's say this D1, D2 strict limit of homomorphisms, by which I mean exactly this. Sorry for people on Zoom, I mean exactly this. Then it also satisfies the NCBV condition. Okay, so the second implication is easier than the first implication. The second implication says, okay, I'm converging strictly, then I satisfy the NCBV condition. Okay, so that's quite easy. You take a sequence of homomorphisms converging strictly in this let's say, let's call it Manhattan sense to F. Okay, so actually these Fk, they converge strictly on almost every lines. So we restrict to almost every horizontal and vertical line. It turns out that the restriction is actually converging. The restriction is actually converging strictly on almost every horizontal and almost every vertical line. Which means that when we go to our grid, because we can choose the grid so it's nice, so in fact the restriction of our sequence to the grid is also converging strictly on that grid, right? Now what this allows us to do is to say, okay, we're converging in L1, there's lots of points which are actually going to be very close in the image. So if I draw a picture of this, it's going to look a little bit like this. So I get my grid, I say, okay, let's work on this particular rectangle over here. Actually, I can find lots of points on this rectangle where Fk of x converges to f of x. Okay, now I want to approximate the image of f of the grid uniformly. So, okay, there are some, f is making some jumps. Now, I want to make an approximation with error, let's say epsilon. So either the jump is big, let's say bigger than 1/100th of epsilon, or it's very small and I basically don't care. So if the jump is very small, it's okay, I can deal with it as if it was continuous. So when I've got a big jump, what I do is, okay, I find some point which satisfies this condition, very close to one side, and very close to the other side of the jump. Right? And then I say, okay, well, what happens by the jump? So the original map is going straight from one point to the other point. My map is going, okay, from some point very close here to another point very close here. And the length is almost exactly the same as the distance between the points. This I get from the strict convergence. So, okay, it can go a little bit by the side, and the distance it can go apart is like the square root of the error of the difference in the lengths. Okay, so set your parameters small enough and you can make this as small as you like. And at the points where you're continuous, so you're starting close, you're ending close, and you're not going very far. So then it's clear that you're staying close all the time. The difficult part is by the jumps. So actually creating approximations which are somehow uniformly converging to the image of what the original map was doing is not so difficult. All you then have to do is like reparameterize it in a suitable way, so that, okay, I know that the shape is more or less the same. Let's just do the shape at the same speed all the way through the grid. Okay, that's exactly what we wanted for the NCBV condition. Okay. The other one is actually a lot more involved, right? So, the first observation. Okay, so for this strict convergence, what do we want? We want convergence in L1 strongly, and we want, let's say, weak star convergence with the total variation also converging to the total variation of the limit. So the L1 convergence is pretty easy. As soon as you make your rectangle small enough, you've got a inf condition, which means that basically, okay, let's say you've got a rectangle which has very small image. Okay, it's a very small rectangle, so most of them have very small image. Some of them have a big image because there's big jumps there. Okay, but that's a very small number of rectangles. Most of the rectangles also have a very small image, and everything which was inside the rectangle is also staying inside the rectangle, and you're doing basically the same. So okay, this is not a problem. Getting L1 convergence is actually quite easy. And anyway, everything's bounded even when you're by a big jump. So you've got a large set where you're very close and a small set where you're not too far away. Okay. So what we're able to do is take a rectangle and say, okay, well, the original map is doing something like this. It's got like a triangle here, and then it's like squashing it flat, and it's got another triangle here. What we are able to do is to find something injective which looks quite similar. Okay. Now in the paper of De Filippis and Fratelli, they also found a way that you can make this injection, which can be very wild, right? So let's say your image is really looking like what we've got here. Then your injectification, I mean, there's no reason why the injectification should also be BV. I mean, it could be, all I'm saying is it should be uniformly close and injective, right? But these very clever colleagues also managed to find a way that you can injectify without making the length much longer, right? And this technique is called arrival grids. So this we use. And then the idea should be, okay, we have some kind of a minimal extension. It's a paper by Aldo Fratelli and Emanuele Radici that saying you're going from a rectangle to some polygon. We found actually the very best way to do that. Okay, so it's if you've got a fixed image and you're going from a rectangle onto that, you fill in your polygon from this rectangle. It's actually the smallest the smallest amount of variation, or very close to it, and you're in fact a homeomorphism. Okay, the problem is this. I'm only telling you exactly what the shape of the polygon should be, not how it's parametrized from the rectangle, and the energy depends on the parametrization of the rectangle. So this is the first problem. The second problem is, potentially, it's not clear why even the shape should be quite close. So look at the red rectangle. Look at the red polygon. It's forcing any horizontal lines to go back this way and come back this way. Whereas in the blue polygon, it's not. They can just go straight through. So potentially, I mean, the amount of energy used to fill up these could be wildly different. And anyway, how do you relate this back to the original map? So we managed to solve these problems by adding lots and lots and lots of extra lines. So we make some rectangles, which we need to get the L1 convergence. And then we look, okay, let's find some lines on which we're also converging strictly. And the energy, So we add these extra lines, which we call guidelines. And let's say, if you imagine I'm working on one particular rectangle of my grid, I say, okay, well, let's look at the horizontal lines. Let's make like a neighborhood here and find which guy is the best, more or less, or close to the best. And then, okay, over here, which guy is more or less close to the best. And if this area is short, then basically I know that I can get from here to here by going a little bit this way, a short guy this way, and a little bit this way. Which means that then when I do the extension here, I can bound this energy in this direction, basically by what's happening on this line, which is then bounded by some average. So I can make this as close as I want. The problem happens when, let's say, here I've got some fractures, I've got some big jump, yeah? Then in the image, this is going to something over here, and it's getting over here. So it's like, you can't have any reasonable bound there. But if you make the set where you have a bad bound very, very, very small, then in the end it doesn't contribute much. So that's what you've got to do. Okay, that's more or less what I'm sort of saying here. Okay, that's more or less what I was trying to explain, what's written here. Okay, yeah. On each rectangle, you know, something like this, you have a nice estimate for the variation, and then you use the lowest ending continuity of the variation, and you get your strict convergence. Let's okay, I should say this D1 plus D2, like this Manhattan type strict convergence. Okay, but this Manhattan type strict convergence doesn't necessarily imply proper strict convergence. If you'd like to see an example, then the picture should look a little bit like this. Imagine you've got a set which you do like this sort of staircase. Now this is going to be the jump set. Everything here goes to point A. Everything here goes to point B. And whenever you cross this jump set, you just jump from A to B. Now, if you imagine this staircase getting finer and finer, you'll actually be doing this Manhattan type convergence to having a jump on the diagonal. Okay, but when you consider the strict convergence, right, so this diagonal is actually always shorter than the steps, like by a factor of the square root of 2, right? So, okay, although you're converging strictly in the D1, D2 sense, because that always sees, it looks at the length, okay, the size of the jump times the length of the projection, which is the same here and here. Okay, but that doesn't work the same as the typical strict convergence. The typical strict convergence says the size of the jump times the length of the line, and the length of this this jump set is always much longer when you're doing with stairs than when you're doing the diagonal. So this Manhattan strict convergence is actually weaker than normal strict convergence, which is not particularly nice. We would like to have like a stronger result, obviously. So the point is this. Let's talk about the second result first. So if you've got a BB plane map which satisfies a slightly stronger condition, the first result says it's actually exactly the same as the original condition, then F is the area strict limit of homomorphisms in BV. And if you have an area strict limit, then it has to satisfy also this slightly stronger condition. Okay. So exactly what this slightly stronger condition is, I'll tell you in a minute. But by the first result, which we put up there, it's actually equivalent to this NCBV condition, which I've been telling you about. Okay. So this actually answers all our questions, right? Because F is a Manhattan strict limit of homomorphisms exactly when it satisfies NCBV. NCBV is equivalent with the slightly stronger condition NCBV star, which is equivalent with the F is an area strict limit of homomorphisms. Okay, so an area strict is stronger than strict, right? So then you've got and then if you're using homomorphisms or diffeomorphisms, this is already known, result of Pratelli-Radici. So in fact, it turns out that we have three classes: Manhattan strict convergence, Manhattan strict closure of BV homomorphisms, strict closure of homomorphisms, area strict closure of homomorphisms. They're all the same class. This is in the end what we've proven. Okay, so how much longer should I go for?
No, you can still maybe 20 minutes.
20 minutes, fine. Lucky you guys. So, in order to prove it, we needed like some fine properties of BV maps. Okay, the first one is Alberti rank 1 theorem. And okay, I'm including this because I found it particularly useful for me, and I didn't know it. So this is why I'm including it. So let's say you've got a polar decomposition of the derivative. F is, or df is some unit function times the total variation of df. Okay, so G is a rank 1 matrix, which means, okay, you can find some vector in the pre-image, which is getting sent onto some vector in the image, basically, for almost every point of the singular part of the derivative, okay? The second part is this Federer-Volpiat theorem, which says, when you're on the jump set, which is, okay, this set SF, this is the blow-up set of the derivative. So where the points where the density of the derivative is infinity, in fact, right? So Hn minus 1, almost all of that is a jump set where you've got a trace on the one side, a trace on the other side, which is f plus, f minus, and you're going across this jump set. You're basically going from the point f plus to f minus, and okay, so it's a blow-up argument. When you blow up at that point, actually you're converging strictly to exactly this map, which is going. Okay, so there's two sort of claims here. As you've got some fracture, your map F is mapping this onto something which looks like this, and as you get closer and closer to this point X, and you blow up, this is also becoming like, so here this fracture is becoming straight, yeah, and okay, so it's perpendicular to this, if I'm correct, yes. So this is the direction going across the fracture. If I remember my vector multiplication correctly, then that's even. And so the fracture is perpendicular to this vector eta, and here you're going from some f minus to f plus, which is also becoming basically yeah. So in other words, and actually you're approaching this limit map in a strict sense, right? Okay. So, what is this NCBV star? This means instead of just injectifying grids which are all vertical and horizontal lines, I take something which is, okay, not just a line, but somehow piecewise linear. And then something's going in the other direction, which are more or less piecewise linear. So you basically imagine a straight grid, and then move it and twist it a little bit, so it's piecewise linear. If I can injectify one, surely I can injectify the other. It's not so hard. What you do is you take your grid, which is now like a non-straight grid. So it means instead of looking like this, now it looks something like this. And what you do is you make little boxes around it all the time. Now, and then you can go horizontal and vertical, and you replace your original image. Instead of injectifying on this original grid, which is non-straight, you've got now, let's say, some very fine straight grid, which you choose parts of, and you can injectify all of the straight grid. So you identify those parts, and just because you keep on going close to your original grid, at points where you're continuous, right? So as long as you're continuous here on this grid, then you're actually staying very close to what the original map was doing. Difficulty comes when you get close to, let's say, some large jump, right? So if you get close to some fracture, we have to use this Federer-Volpier theorem, which says, okay, so there's some fracture there which you're crossing, so you can actually cross at some other point which is very close, and it's doing a very similar jump to what the original map was doing. Right? That's this here. This is talking about some strict convergence to the jump. So as when you get to some big jump, you find, okay, I find another place to cross where I'll cross going either vertically or horizontally. One of them has got to work, and you're doing a jump of a similar size. Okay, so we see that if I'm going with a straight grid or a not straight grid, it's the same. So now the question is, how do I construct, given a area strict limit? No, yeah. Given a function which satisfies this NCBV star condition, how do I construct a sequence of homomorphisms which converge area strict to this map? Okay, it's a very detailed construction. Already, if you want to approximate a homeomorphism in W11, already this is like 40 pages or so to do the construction. Not necessarily very easy. So compared to that, the first thing which we have to do is separate out the parts where we are where we've got a lot of the singular part of the derivative. Okay. So on our square Q, we find some set S where basically, okay, the singular part of the derivative almost entirely lives only on S, and the absolutely continuous part of S is very small. Well, seeing as the singular part of the derivative, okay, it's definitely supported on a set of zero measure, and the absolutely continuous part of the derivative is okay. So outside of this set S, where we've got lots of singular derivative, it's not so difficult. Well, it's not necessarily easy, but you can follow principles which have already been done. There are some extension theorems and so on. So perhaps your mapping already looks like a linear map. Then if it's a nice linear map, it's quite easy. If it's a degenerate linear map, then there are some extension theorems. If the image looks completely crazy, then there are other theorems. But you can basically use this minimal extension, which was given by Fratelli and Radici, to extend, because you've got a rectangle going onto some kind of shape. I'm not saying it's easy, but it's sort of been done before. It's not the original part of this particular research. Okay, so then you reduce down to some set S, which we cover with squares or rectangles, I should say. And on many of these rectangles, we have a Lebesgue type estimate. Okay, let me draw a picture over here. So here's the set S, and we separate it out into lots of little rectangles. Now, when we make them small enough, we can actually have these types of estimates on each of these little squares, which I'm talking about over here. Right. So we're looking for places where the singular derivative is living. We have this Alberti rank 1 theorem, which tells me that, okay, the singular part of the derivative should basically look like this. Okay, we're talking about nice measures, so we actually have some differentiability of the measures, and we have some Lebesgue type estimate which says, okay, actually, my singular part of the derivative is really close to some constant, times by the total variation up to some small error. And I'm not seeing much of the absolutely continuous part of the derivative either. The absolutely continuous part of the derivative is small with respect to the singular part of the derivative. So when I say most of the squares, I mean energy-wise, most of the squares, you have some estimate like this, as soon as you make them small enough, right? So you're using some fine properties. Then, when you have a rectangle like this, where you're basically all sending everything in one direction, yeah? It's the rank 1 matrix image of a square, in some sense. Then what you have to do is take your square and make rectangles which are parallel and perpendicular to this vector f, which is telling you where the derivative is coming from. And when you've got a rectangle switch like this, then you can use this already known minimal extension. And then you have to hope that the bit which is left over, it's actually now not got a lot of energy left in it. So you have to be a little bit careful to make sure that almost all of the energy is taken up by these rectangles which you create, and the rest of the set has got only a little bit of energy, and then you use a less sophisticated extension there. But it's not taking up much of the energy because it's only a small set. Okay, so that's basically how we approach this problem, and then maybe if there's any questions about that, I can answer that afterwards. So there's still open questions. We could look at what happens if you assume that the inverse is also in, let's say, Sobolev. Or okay, well, so in the planar case, it's already known that it's in BV, right? But okay, yeah, that's not obvious. So the homomorphism. So when you've got a homomorphism in BV in the plane, the inverse is also a BV homomorphism. This is known, but when you go to the limit, it's not clear. But this is something which we proved with Stander, Apple, and Manuel that it is actually true. Okay, right. So there's already some models for which create fractures and cavities by Morocaral and Henao, and so okay, we have this model which goes through this relaxation argument, and the question is how close are they to each other? I suppose they're actually a little bit different. And then also we can look at different behaviors close to the boundary, even accumulations at the boundary, which we haven't done yet. And also then there's also possibility for higher dimensions, which is typically these days nobody really knows what to do in these questions in higher dimensions yet. Okay, and then there's some papers there, very important papers. And thank you.
Yeah, thank you.